Welcome to this video. My name is Mark Scythian. The date today is July 7th, 2024. This video is going to focus on techniques to derive alternate equations. So assume that you're working with Newton's second law of motion. Force is equal to mass times acceleration. We can also find the equivalence for acceleration, which is the change in velocity divided into time, as well as distance divided into time squared. And then, of course, algebraically rearranging acceleration from F equals ma, we get force divided into mass. So we could also derive an alternate set of equations from the F equals ma equation, such as mass times the quantity of distance divided into time squared, which will simplify into force is equal to md, mass times distance, divided into time squared. So we'll call the first fundamental equation as it is. Then we have equation number 2 here. So a third equation could also be the mass component could be rearranged as force divided into acceleration, F over A, then multiply times the quantity of d squared, d divided into t squared. So we have F is equal to FA times the ratio of distance divided into time squared. This then simplifies into F is equal to force times distance divided into AT squared. Making this into one line, we get force times acceleration times time is equal to force times distance. We can cancel both force values out, and we're left with AT squared is equal to D. Then extracting our force component out of A, so F over M times T squared is equal to D. So then we have F T squared over M is equal to D, and then M mass times distance is equal to force times time squared, and so we get the redundancy. So all we have left is the delta V over T to derive an alternate equation from. So we could take force is equal to F over A times delta V, change in velocity over time. So this becomes force times the change in velocity divided into AT equals F. Force times acceleration times time is equal to force times change in velocity so we're left with AT is equal to delta V, and then again taking the F is equal to, the A is equal to F over M times T is equal to delta V. Then we have Ft over M is equal to delta V, and then F T is equal to M times change in velocity, and then we can divide this into T. So F is also equal to mass times change in velocity divided into T. So another equation to work with is the kinetic energy. So kinetic energy is equal to 1/2 times mass times velocity squared. So we could redefine mass as force divided into acceleration. So this becomes 1/2 times force divided into acceleration times velocity squared. So then KE is equal to force times velocity squared over A, actually over 2A. So we could also redefine velocity as distance divided by time. So if we were to re-equate kinetic energy as force times velocity squared divided into 2A, then multiply times distance divided by time is velocity quantity squared. Kinetic energy is also equal to force times velocity squared over 2A times distance squared divided into time squared. So this then simplifies to kinetic energy is equal to force times velocity squared d squared over 2 times acceleration t squared. So if we're working with the area of a circle, pi r squared, we could also redefine radius as diameter divided by 2. Should make this a capital D, as it is diameter divided by 2. So we could also make the area of a circle equal to pi quantity times the quantity of diameter divided by 2 quantity squared. So this then simplifies to pi times d squared over 4. So this becomes area of a circle is equal to pi d squared over 4 We also have a correlation with the circumference formula. Circumference is equal to pi times diameter. So we could solve for d, which is circumference divided into pi times d there. So then we could find the equivalent to d squared. And this correlates or translates to c squared over pi squared. So then a third alternate derivation for the area of a circle as area of a circle is equal to pi times c squared, or circumference squared, divided into pi squared, then into 4. So upon simplifying, the area of a circle is also equal to circumference squared divided into pi, then divided into 4. So c squared, as in circumference squared, divided into pi, then divided into 4. So we get this reciprocal of the second fraction. So this becomes circumference squared divided into 4 pi is also equal to the area of a circle. Call this number 4. Actually, it was part of 3. So we have one more example here. It could be the Einstein-Rosen bridge, which is E energy is equal to mass times the speed of light squared. So we could redefine mass as force divided into acceleration. So this then could be derived into force divided into acceleration times the speed of light squared. So E energy is also equal to force times the speed of light squared divided into A. So we can call that number 2. So a third derived alternate equation could also equal a redefinition of acceleration d over t squared, and we also have the change in velocity divided by time for acceleration, so we could redefine it as force times the speed of light squared divided into distance divided into time squared. So this becomes fc squared over 1, and we'll get this reciprocal ahead of time, so this becomes t squared over d, or time squared divided into distance. So we have fc squared t squared over d So E is also equal to force times the speed of light squared times t squared divided into distance. So if we look back at any of these equations, mass could be A over F over A, but then we have F over A, yeah, we have redundancy. So you're able to obtain derived alternate equations from a base fundamental concept. And I guess the last one we can do is the concept of pressure. So of course, either dynamic or static, but pressure is either a dynamic or a static force divided into a certain amount of area. So example, pounds force per square inch, PSI. And that could be gauge, static, that could be dynamic, pressure, the pressure during motion, backing pressure, etc. But we also know that force is mass times acceleration. So we could set up a dynamic pressure equivalency to P is equal to F over A. So of course we could substitute and just rewrite it as P is equal to MA over area, mass times acceleration divided into area. So that becomes a second derived equation. And then we also have the force divided into acceleration is mass. Which then becomes redundant, right? If we take it times A, we lose that. Okay, so we have P times area. Area is also F over P to get A. So we could test that application. MA over F over P is equal to P, so then we flip these around. MA times P over P over F equal P. So we have MAP over F is equal to P. PF is equal to MAP, and then we cancel both P's out, and then we have only the Newtonian force component. So hence a technique to prove redundancy as well. So we have to find something that's equal or equivalent, but also a different application, different components, but the same equality. And so we know acceleration is d over t squared, then times mass over 1. So that's ma. This is distance times mass divided into t squared. So we divide it by a, so we get its reciprocal 1 over a. This becomes dm over t squared. A is equal to p. So if you had a dynamic pressure, you'd have a certain distance times the mass divided into the time squared times the cross-sectional area would also equal the pressure. So we'll call this number 3. So these are just some techniques to derive alternate equations from conceptual relationships or formulas. So again, all of these equations are equal to each other's definition and value, but they have a different component expression, hence the techniques to derive alternate equations. Thank you for watching this video and have a great day.